Hello everyone, thank you for joining us today, and I wish you all a very warm welcome to today's presentation. My name is John Norman, I'm Head of Marketing at Optibrium and moderator for this webinar. And I'm delighted to be joined by my colleague and CEO of Optibrium, Matt Siegel. And Matt will be presenting Cerella, reduce the time and cost of your discovery cycles with deep learning. Matt, I will now hand things over to you.
Hi, John. Thank you very much. It's a great pleasure to see so many of you here in the audience today. And I'm going to be telling you about our Sorella platform and how it can use AI insights to help you to optimize your discovery workflows. I'll give a bit of an introduction to some of the challenges and how Sorella addresses those. Then I'm going to give you a live demonstration to show you how that can actually work in practice. But then I'll tell you a bit about what's going on behind the scenes. Some of you have been to previous webinars where we've been looking at this deep learning method called Alchemite. I'll give you a bit more background there. But then I'll also show you some example applications. And I think it's really important that while there's a lot of hype around AI and drug discovery, to really ground the methods that we use in reality and show that they work actually in practice. And we'll draw a few conclusions at the end before we go on to address the questions. So first of all, some of the challenges that I'm sure you've encountered in the course of your drug discovery projects. So it's expensive and time consuming to acquire data on your compounds. And it's just impossible to measure all of the compounds and all of the assays of interest. So, how can you actually make the most of the data that you have? Furthermore, the data that we do have has a lot of variability. We know there are artifacts, experimental errors, and it's very easy to be led astray. I think there's an interesting bit of SAR or a really remarkable result and spend a lot of time sort of chasing that down a rabbit hole. And when we have to make decisions about what experiments to run, how to use our time and resources, we need to think carefully about what is the most valuable data to measure. What data will actually give us the most information with which we can make decisions about the progression of compounds. And then, of course, what we're interested in doing is designing new compounds as well. And we're all familiar with using predictive models for that. So how can you use the limited data that we do have to make better predictions for new compound designs, and of course, from that, choose the best compounds for synthesis and testing. And what we're going to be illustrating today is how the deep learning method within Cerella can really help to answer some of these challenges and really reduce the time and costs of the discovery cycles in your projects. So we'll look at the idea of filling in that sparse data, filling in those gaps, and proactively highlighting high quality compounds. This is a method called data imputation, using the data we have already to fill in the gaps with improved accuracy. We'll look at how we can increase the confidence in the decisions that we're making, particularly identify hidden opportunities, outliers that we might have missed due to false negatives or potential errors that could lead us astray. And how we can use the insights that artificial intelligence brings to help with the planning of experiments and focus on that most valuable data, the most valuable experimental measurements to make to better predict and better identify the compounds that will succeed downstream. And then we'll look at how we can gain more value from the compound data that we have in making predictions, particularly of complex experimental endpoints, whether that be from, say, phenotypic cell-based screens or even in vivo properties that are often intractable with conventional QSAR modeling. And we'll also demonstrate how the underlying method that's implemented in Cerella can actually work even on small sort of individual project data sets, but also scale to tackle sort of global compound data repositories. So how do we do this? Let me give you an introduction to Cerella, the concept behind it, some of the applications, and then we'll give you a live demonstration before digging into some of the sort of nuts and bolts beneath the surface. So what is Cerella? Well, Cerella is a platform for active learning in drug discovery. What that means is it relies on the latest data and is constantly updating so that the predictions and the imputations that you're using are based on the latest information. To do this, it connects with your data sources, whether it be your data mart and ELN, whatever database system that you use. It loads data from those data sources into Sorella, and what we have here is a sparse matrix of data. So we have some compounds up this axis and experiments along this axis, and of course, as we just described, no compound has been measured in every experiment, and no experiment has been run on every compound. And in fact, in a typical sort of global pharma data set, less than 1% of those possible measurements have actually been made. In importing that data, it also does all of that sort of preparation and cleaning that we know is necessary to get a good model. It transforms into appropriate units for model building. It can do aggregation and cleaning of that data by whatever business rules that you use. It then takes that data, that sparse and noisy experimental data, and uses a method called Alchemite that we'll discuss a little bit later to build models and update those models as new data become available. One of the applications of this deep learning model is, as I mentioned, to fill in all of those gaps, to use the sparse data that we have available to fill in the blanks, sort of illustrated here by these purple squares. And I guess another challenge that suggests is, well, if that initial matrix of experimental data, the green squares, was less than 1% complete, and we fill in the other 99%, suddenly we've got 100 times more data to deal with. And we have what we describe as the massive matrix challenge. It's true big data. It can contain, tens of billions of data points. And so it's really important that we can scale to actually store and search and retrieve the most interesting results in a very efficient way. And then those models and the results need to be easily accessible. Today, I'll be demonstrating the access through our StarDrop software. But all of these endpoints, these models, these methods are accessible by any platform that you wish to use. It's an industry standard RESTful API, so you can sort of plug and play as you require to use whatever platform you prefer to analyze and draw out the most interesting results. So that's the sort of the Sorella engine. How can we actually use it? What applications can we look at? Well, the first that I just mentioned is filling in the missing data for your compounds, but highlighting high quality compounds in a very proactive way. What you don't want is just to have this massive matrix of data dumped on your desktop to sort of slice and dice and try to find the interesting compounds. So one of the sort of workflows you might imagine is driven by something we very often do, which is querying a database. This is an example of a query. We're looking for a compound that is active against our target. It has good permeability in CACO2 cells and good solubility. And of course, what we would normally do, we can go to our database and we can retrieve the compounds that have been measured to meet those criteria. But now, just by checking a single box here, we can actually return much, much richer data. What we can do is look at those imputed values, the values that have been filled in, and bring out compounds that are also confidently predicted to meet your criteria. So you can see here, the white squares are those that have been measured, the values that have been measured, whereas these blue squares are the filled in values, the imputed values by the Alchemite algorithm. And it's saying, hey, look, these are really interesting compounds. You might like to test them to validate that hypothesis because they could be really important for your project. Another example application is to identify those pesky experimental outliers. We know that we make errors in our experiments, there are impurities, whatever it might be, that can give rise to incorrect results. So here you can see on the right-hand side these little purple squares. These are measured values that have been flagged up as being highly unlikely based on the underlying model and the confidence values that are generated by that. It's saying, hey, look, you might want to check this. It could be an experimental error. You might want to retest that compound. Or on the positive side, it might be unexpected structure-activity relationship that could really give you a big clue as to how to guide the optimization of your compounds. If you click into this, you can actually see a more detailed representation. Here you can see this blue histogram is a probability distribution that's returned by the model. We'll talk more about that later. What this is saying is that this compound is very likely to be active. You can see the peak in the probability distribution over here to the right. The measured value, though, is this red bar. What this is saying is that this looks to be an outlier. It looks to be way off on the negative tail of that distribution. It's a potential false negative. And we know that's a real challenge. You know, whenever we do a screen, we know there are false negatives. The question is, where do you go looking for them? Which compounds do you retest to make sure that you're not missing potentially valuable starting points or important structure-activity relationships? We mentioned, guiding the prioritization of experimental work as well. What you'll see is that you can select one or more sort of downstream assays or experiments that you want to do. Here I'm showing, say, a cell-based activity, a phenotypic screen. And I can say, well, okay, this is the assay that I want to pick the best compounds for. What is the most valuable earlier stage measurements that I can make? So here are some maybe higher throughput or lower cost assays that I can run. And maybe I want to make, say, 20 or 30 measurements. You can choose how many you want or explore that variation. And it will say, right, well, if that's the experimental effort that you want to invest, here are the most important assays to run that will better inform the choice of compounds for that downstream, if you like, target assay. So here you can see this histogram. It's saying that the two big bars actually correspond to activity against the target and CACO2 permeability. So those look to be the assays that will give you the most information. And you can even sort of click on one of these bars and it will tell you the specific compounds that will also add the most value if measured in that assay. So exploring that chemical diversity appropriately to find the best compounds and make more accurate predictions across the entire data set. That helps us to choose then the best compounds to go into those expensive downstream experiments and hopefully find the winner for our project. And of course, all of these endpoints are available as virtual models, so running on compounds that have not yet been synthesized and tested. So you can take a virtual library, make predictions and say, which of these compounds are most important in terms of synthesis and then testing to validate that predicted hypothesis. So I'm going to actually show you some of these workflows live in just a moment. But before I do, I just want to say one more word about the sort of architecture underlying Sorella. So when we developed this, I mentioned the importance of scalability. So it will work from everything from a single project data set with hundreds or thousands of compounds up to a global scale data set containing millions. So scalability is really important. But the other side of that is security. Your data is critically important, extremely valuable to you, and so that security is really important. And so we've developed this hybrid architecture that gains the best of both worlds. What you can see here on the right-hand side is what we call the blue zone. The blue zone is where all the sensitive data and processing goes on, so the data management system. This is where what we call the query service connects with the databases and brings in and updates the latest data. That is then passed to the Cerella service, which does a number of very important things. The first thing it does is calculate any compound descriptors that we want to use in building these models. Then it removes the compound structures from the data set entirely. It takes any proprietary sort of compound identifiers and replaces them with a sort of a pseudo-random anonymous identifier. It then takes any assay names or any information about the assays and replaces those with, again, pseudo-random anonymous identifiers for the experimental assays and endpoints. So it strips out any information about the meaning of the data and the relevance to the compound structures. In fact, it even removes the names of the descriptors, so it's just an anonymous matrix of data. That is then encrypted and passed up to what we call the green zone. The green zone provides that scalability for modeling and handling this massive matrix. So this is where Alchemite runs and where the massive matrix resides to make it very easy to sort of search and scale across that. And so this division means there's huge flexibility in how this can be deployed. I'm showing an example here where for the blue zone can be on your private network where all that sensitive information is processed. The green zone could be in a virtual private cloud, unique to your organization, but sitting in a cloud where you can gain from that very cost-effective scalability. The other thing that happens, of course, is once the data comes back to the blue zone, you retrieve the interesting results. The Cerella service sort of glues it all back together with the compound structures, the assay information, because, of course, that's where you as the user sit. You want to see all of those data, those predictions in context with your compound structures and assay information. So you can see how we get the sort of best of both worlds. Now, both of these zones can be employed to be deployed completely in your cloud or on your premises. We can host both of them if you want, but this division enables us to also sort of split this up, whatever works best for your requirements. Okay, so that's enough about the platform in concept. Let's actually have a look in practice at how we can actually use this information. So now what I'm going to do is actually give you a demonstration through our Stardrop software. I should say that I'm using Stardrop as the front end, as the interface to this, but please be aware that whatever platform you use to analyze and visualize your data, it will just plug in and use exactly the same results that you'll see within Stardrop. So it's not constrained in any way. So let's get out of the slides. And this is our Stardrop software. I won't spend a lot of time giving you a tour of Stardrop. I think many of you in the audience know it already. But what I wanted to do is illustrate some of these workflows that I described in the slides. So let's think of something we might typically do. This is actually using a data set. It's a public domain data set published by Medicines for Malaria Ventures. It's called the Pathogen Box, and it contains compounds with data across a wide range of different assays for developing world and neglected diseases, as well as sort of ADME and physicochemical properties. So if we had a particular project we wanted to retrieve some interesting compounds to explore further, we could do a query of a database. So I'm going to use the query interface in Stardrop to perform a query. So here's an example of a query. This is targeting a TB compound. So we've got criteria for activity against TB in 2 different assay conditions. And in both cases, we're looking for compounds with better than 1 micromolar activity. So if we've measured the compounds and they meet those criteria, we'll retrieve that in the query. Along the way, I'm also going to bring back some ADME data, so solubility, permeability in Pampa, some stability data on in mouse liver microsomes and mouse hepatocytes, and so on. And if I click OK, this is going to go to the database, just as we're familiar, and retrieve the compounds that have been measured to meet those criteria and bring back the additional data. And you'll see within a couple of seconds, it just brings back 7 compounds. Here you can see those 2 measured activities in these 2 columns here. In both cases, each of these compounds meet those activity criteria. We've got a bit of ADME data, but I guess something we're all familiar with. A lot of that data hasn't been measured yet. It's missing. So this isn't a very exciting starting point to find a high quality hit or lead for this project. We've got very little data to explore and only a handful of compounds to look at. So let's see if we use Sorella to do the same thing. So again, I'm just going to go right back to exactly the same query that I ran before. That'll just take a second to pop up. And now the only thing I'm going to change is I'm going to check this one box that says search Sorella values. So now this is going to go to the massive matrix, the filled in data for these compounds. I click OK. Again, it just takes a few seconds. And what you'll see is up pops not 7 results, but 50 compounds that are being highlighted as likely to meet these criteria. Now, some of them we've seen before. So here you can see in row 6, both of those activity measurements have been made, and as we saw before, both of them meet those activity criteria better than 1 micromolar. But you'll see another example here, row 12. This has been measured in one of those assays, but hasn't actually made it to the second assay. This has been filled in. Again, the blue squares here are those that have been filled in automatically by Cerella. This looks like a really interesting compound, active in both of the assays. There's another example just below it that's been measured in the second assay, but not the first. So these are compounds that would have been entirely missed based purely on what had been measured so far. We might not have found these interesting compounds to explore further. And of course, some of these compounds have never made it to these TB assays at all, but based on all of the other data, we've been able to infer or impute those missing values, and it says, hey, these might be worth exploring in these TB assays as well. So we've got a much richer data set, many more compounds, and all of this missing assay data for ADME properties has also been filled in. Again, the blue squares there. So it enables us to look for compounds not only for activity, but with a good balance of physicochemical and ADME properties. If I scroll down a little bit further, we see some examples of those purple squares that I mentioned in my slides. Now, these are measurements that have actually been made for these compounds, but are being flagged up as highly uncertain. So here's an example in this row here. Both of these assays have returned a result of greater than 50 micromolar. Now, of course, normally that wouldn't be returned by the query at all. But here it's saying, look, I'm going to show you this compound because these results look highly unlikely. So we can say, well, really? Okay, let's find out a little bit more. So if I right click on that cell, I can ask to show the underlying probability distribution. And what you can see now, up pops this little histogram. Here in blue is the distribution, the probability distribution generated by the model. This is heavily weighted to the left. It's heavily weighted towards, a highly active compound with sort of low micromolar or even submicromolar activity. The actual experimental measurement is all the way out here at 50. That is greater than 50. And here's a sort of a lower confidence bound, the little dotted line on that measured activity. So this looks like it might be one of those dreaded false negatives, a potential missed opportunity. So we can easily identify that as a compound that is very valuable in order to retest and maybe find that a new starting point. So we've got a lot of data. We've seen there's probabilities and uncertainty in all of this data. Both experimental and predicted data have uncertainties, of course. So one of the things we could do is try to bring that together and find compounds that are likely to have a good balance of properties. So what I'm going to do is apply a multi-parameter optimization strategy to this data set and look for compounds, again, that are active in both of these TB assays, but also with good metabolic stability, good permeability, and good solubility. This is one of the features of StarDrop. This is a method we call probabilistic scoring. I won't dwell on it here, but we have numerous webinars and examples of this if you're interested in finding out more. But what I want to use this for is to prioritize those compounds that are most likely to achieve these criteria, taking into account the data against the criteria that we've set, but also that underlying uncertainty, those probability distributions that I described. It just takes a few seconds to run, and what you'll see is a score appears for each compound. If we sort these into descending order and scroll to the top, you'll find the compounds with that best overall chance of success here, sort of 20% or more, which I guess at an early stage of a project, given all that uncertainty, is a pretty good result. You can also see the little histograms tell you about what are the critical issues affecting a compound, and you can also see the same information in this sort of heat map here. So if we just look at some of these top scoring compounds, what you can see is, for example, row 2, most of these properties have actually been measured. You can see the white cells here, those are the experimental measurements, but this top ranked compound, which is predicted with confidence to be at least as good as this one below, actually most of the data hasn't been measured for that compound. So hey, that's a new opportunity we might have missed. I think it is important to remember, though, that like any prediction, like any experimental piece of data, there is uncertainty. I'll just show you that by turning on the statistics view here in StarDrop. What you can see now is the light half of the columns contain the actual measured or predicted value. The gray half contains the uncertainty. So you can see here these two filled in imputed values here at the top. They're very good, about 0.3 micromolar, but they do have a bit more uncertainty than the experimental measurements. We have to be honest about that. You can see a factor of 2.5 versus a factor of 2. Even more so, you can see that one of these pieces of data, this predicted value, has a lot of uncertainty, a factor of 16 really. So this is the model saying, hey, look, be careful about this. This would be a priority to test to see, if that value is correct. Because if it is, this looks like a really good compound. So again, it helps us to choose, in that sense, the most valuable experiments to run. So you can do this by sort of eyeballing and looking at that and saying, hey, interesting compound, here's some important experiments to run. But we can answer that question or ask that question in a more general sense, as I described in the slides. So let me turn off the uncertainties for a minute and scroll here to the right. What I didn't tell you is at the same time, I brought back data on two different TB endpoints. These are actually MIC90 values. This column here, the blue one at the top, this is against a non-replicating form of TB. The next one across is actually an MIC90 against a replicating form. So this might be one of those assays that is perhaps performed downstream. Obviously a very important assay, so something that we might like to choose the best compounds and not screen everything in those assays. And the more accurately we can choose those compounds, the better we can use our resources and save time and effort. So what I can do is say, right, if I want to make better predictions for these two assays, for the compounds in this data set, what experimental measurements could I make using some of those early stage assays that would best inform that decision? And so I'm going to go across here and I'm going to ask Cerella to suggest the most important measurements. Now, I don't want to choose the assays I'm picking for, so I'll just choose the other 6 assays. And I'll just say, for the sake of argument, we'll make 50 suggestions, the 50 most valuable measurements to make. If I click OK, away it goes. Just takes a few seconds and up pop the results. So as I showed you in the slides, what I have is a histogram. I guess the first thing that's interesting is from those 6 assays, it's actually only identified 2 as being relevant. Now, it's not a huge surprise because both of these are the 2 activity, the earlier stage MIC assays that we actually looked at originally. So of course, the most important assays to predict MIC90 is likely to be activity. What's more interesting is that the large majority of those actually come from just a single assay. So here you can see this is the assay being run in DPPC and cholesterol. And 36 of those 50 suggestions come from that single assay. So this assay clearly has much more relevance, much more importance to the prediction of those downstream endpoints. And again, if I select that bar, you can see above, here's a table of the specific compounds. The compounds are selected here. We can scroll through. And in fact, what's very interesting is 32 of the top 50 are, it's only the 33rd that is actually selected from a different assay. So 32 of those top 50, the first 32 of those top 50, excuse me, are from that single assay. So clearly that would be the most important experiment to run. It's a simple example, but hopefully you can see that. Of course, having found that out, you can just export that list of compounds and assays and send it off and ask for those to be prioritized and get that data as soon as possible. That then feeds back into the system, as we mentioned, and is used to more accurately predict those downstream endpoints that we're interested in. Okay, so that helps us to sort of think about streamlining our experiments and our screening cascade, make those more efficient. The last thing I'll just show you is, of course, virtual prediction. So we often end up in a situation where we're thinking of new compounds to make. So I'm just going to switch tack a little bit onto a virtual library of compounds. This is actually targeting an anti-malarial in this particular case. And to give credit where credit is due, this is a series of compounds that was published by the University of Cape Town recently. And I just thought I'd use it as an interesting example. But of course, this could be any virtual library. Again, this is quite small, just so it runs super quick. But you can do tens or hundreds of thousands of compounds, even more if you wanted to. So if I go to the Models tab in Stardrop, again, I'm using Stardrop to illustrate this, but the models are available through a RESTful API, so it can be run from anywhere. What you'll see under Sorella, for each of those individual experimental endpoints that we saw in the database, there's also a model available. Just scroll through here and see there's about 50 different models available here. And so I can pick the ones that are most relevant to this particular project. So in this case, we're looking for an antimalarial with a good spectrum of activity against drug-sensitive and drug-resistant malaria. So I'll select a few different strains here to run. But I guess, as always, we're interested in some other properties. One thing, for example, we're very interested in is looking at selectivity between antimalarial activity and general cytotoxicity. So I'm also going to select cytotoxicity in HepG2 cells. Other things I might be interested in is fraction unbound in mouse plasma, because the mouse model is very commonly used. A thing we always like to keep an eye on, avoiding hERG inhibition, so I can tick that box. And I guess just as one last illustration, oops, if I can type mouse liver microsomal stability, let's look at intrinsic clearance in mouse liver microsomes as well. So I've selected a broad range of different models really just to illustrate that. And with the click of the button, it sends it off to Cerella and it just takes a few seconds. Now you can see these blue squares have been filled, and now they're all blue because these are virtual compounds. There's no experimental data for these compounds at all. And you can see we have predictions for all of these endpoints for all the compounds in this series. Now, I mentioned that selectivity was important, so let me just calculate the selectivity. Again, this is just using a star drop feature. I actually predefined a function to calculate the selectivity between HepG2 and antimalarial activity, so I'll just add that column. And then, similar to the example I showed you before, I'll bring that data together using a multi-parameter scoring profile. And that just takes a few seconds, and I can sort that in descending order to find the highest scoring compounds come to the top. So again, we can use these predictive models. We can very quickly find the compounds that are not only predicted to be active, but also to have good physicochemical and ADME properties, and choose the ones we want to synthesize and test to validate that hypothesis. The last thing, having found some interesting compounds, clearly we like to think of where to go next and think about design. So really just to point out that if we look at these compounds in more detail, we can actually work with these models in a very interactive way. So here we have our sort of antimalarial profile. I guess the selectivity index is okay, but we'd like it to be better. And so very, very easily, you can just edit here, and you'll see as soon as you type, within a matter of seconds, those results come back, and you can see the impact it has on the overall profile of properties. You can edit away to your heart's content and start dreaming of all the compounds you might like to make, and thinking about where to go next in your sort of chemistry space, if you like. So hopefully that sort of illustrates some of the potential applications. Again, that was just a really quick tour, if you like, but hopefully you can get a feel for how we can sort of interact with these in a a very sort of natural way to get the results that we're interested in. All right. So dropping back into the slides. Hopefully you've seen how this can immediately help and have all this information at your fingertips. The next question, how does it all work? It's all very well showing this, but clearly underneath it needs to be some really rigorous science. So I'm just going to say a few words about this method. It's called Alchemite, that actually powers Sorella beneath the surface. And then I'll also give you some case studies that show the practical applications in a number of different contexts. So the first thing, I mentioned this word imputation, this idea of filling in the blanks. So I just wanted to give a little bit more background about that. So we're all very familiar with predictive models. Typically, we use things like QSAR models, and these models use features to make predictions, in our case, about a compound. So typically, we calculate molecular descriptors of some sort, and if we've got a matrix here of compounds and descriptors, these little orange cells represent the calculated descriptors, and we can calculate every descriptor for every compound. And so this is a complete matrix of data. We can feed into our favorite modeling method, showing here, for example, a random forest, but it could be an SVM, a deep neural network, a Gaussian process, whatever you use. And we can build and run models for one or more endpoints. So these purple squares represent those predictions for all the different endpoints for all those different compounds. Imputation is quite different. What it does is it uses the data we have available, this sparse data that I described, as input into a model. And you can see that most of that data is missing. What it does is use that limited data to fill in the blanks. Again, the purple squares on the right-hand side. So that's the idea of imputing or filling in those missing values. So it's quite a different process from a conventional sort of QSAR model. And the specific method we use is called Alchemite. Alchemite is actually through a collaboration with a company called Intelligens. Intelligens is a spin out of Cambridge University here in the UK. Their background is primarily in material science, and they've had great success discovering new materials and working with a whole range of companies. And my favorite anecdote is that they have 5 patented nickel superalloys in collaboration with Rolls-Royce for jet engine turbine blade manufacture. But we have an exclusive partnership with them to take this approach and apply it in the context of drug discovery. And so Alchemite can still take the descriptors that we commonly use, so it can still learn from that structure-activity relationship between the compounds and these different experimental assays or endpoints. But it can also take this sparse data as input. What that means is, even though most of the data is missing, where it is available, it learns directly from the relationships between these endpoints. And what that means is it can make much better use of this sparse and noisy data that we're plagued with in drug discovery than conventional QSAR models. And I'll show you some examples of that in a minute. So it uses that, as I mentioned, to fill in the gaps, these imputed values in purple on the right-hand side. What we've also discovered, and you can see more examples in the publications below, is that you can use this to make predictions for virtual compounds as well. So you can basically tell the model that this matrix will be empty. We don't have any experimental data, just use the descriptors. And it still makes very high quality predictions for all those different endpoints. The example I showed you in the antimalarial case. I'm not going into a huge amount of detail here in the interest of time, but 2 publications in Journal of Chemical Information and Modeling provide a lot more detail on the algorithm and the methods underlying this. The second really important feature, we talked a lot about uncertainty and probability distributions, is Alchemite doesn't just generate a number and say, here you go. What it does is it generates a probability distribution over possible predicted values for each individual prediction. What this means is it can highlight the most confident prediction, the ones with the least uncertainty, for us to use in our decision making. So sometimes you see a distribution like the one here on the right-hand side. It's very broad and smeared out. That's the model saying, I think the value is somewhere around here, but there's a big error bar on this. I just don't have enough information to make a really confident prediction. But in many cases, what you see are these very sharply peaked probability distributions. That's the model saying, yep, I've got a lot of confidence in this value. It's got a small error bar. You can use it and you can trust it. And what we've demonstrated, I'll show you some examples of this, is that there's a very strong correlation between the model's estimate of its uncertainty and the observed accuracy in each individual prediction. So it helps us to confidently target high quality compounds, but also, as you saw, to prioritize experimental resources. Where there is the greatest uncertainty, you've got these broad distributions, that's where experimental data will add the most value. And so we can use it to suggest the most valuable experimental measurements, as I demonstrated. Okay, so that's a little bit about the theory. Before we get to the Q&A, the next question, of course, is, does it work? And what I'm going to do is just show you some snapshots of example applications across a range of different drug discovery projects and objectives. In each case, I'll also show you where you can go either to publications or to more detailed webinars that really flesh out these examples. So the first example was actually a collaboration with Constellation Pharmaceuticals. What was really interesting here, I guess similar to the demo I just gave you with the pathogen box data, this was a very heterogeneous data set. So it included target activities against on and off targets for a couple of different projects, as well as a broad range of ADME properties that they were interested in. This is an example of a relatively small data set. By the end of this project, there were only about 2,500 compounds across two drug discovery projects. In fact, the first one started with only a very small data set, and that's across these 18 endpoints. So one of the challenges of deep learning is that very often these algorithms only work on very large data sets to gain any value over conventional QSAR methods. What we were able to demonstrate here, and again, there's lots more details in our publication in Journal of Chemical Information and Modeling, is that even with this small data set, this deep learning imputation approach significantly improves the accuracy over conventional QSAR methods. So here you can see the best QSAR method across these 18 endpoints averaged an R-squared of 0.5, whereas Alchemite got an R-squared of 0.72. And you can see here for each individual endpoint, I'm showing the blue bar is the best QSAR method. We actually use 4 different QSAR methods, and I'm showing the best result on the test set in each case. This orange bars here are from a single Alchemite model built across all this data in a single model and across 2 projects and all these different endpoints. Now, you could hear much more about it as well in a webinar we recorded back in April last year, actually. We were joined by Julian Develle, who's Vice President of Drug Discovery at Constellation, and he shared some examples of how they found these results to be useful. And one of the things that he highlighted was that where they looked at the confident predictions from Sorella, if they had rejected the compounds that were confidently predicted to be inactive, they would have missed very few false negatives. They could have actually saved a huge amount of time and effort in synthesizing unnecessary compounds. I think he suggested it was something like 12 FTEs for 2 months, which conservatively is about $600,000 in saved time. So using that confidence is really important. Where there's uncertainty, yes, you want to go measure it, but if you've got confidence, you can really rely on those results. Another example, this is a little bit of a teaser for the webinar that John mentioned. We'll be running in just a few weeks on the 30th of March that will talk about this in much more detail. This was a collaboration with the University of Dundee, where we were actually demonstrating the ability to learn from a global data set to guide individual project optimization. So we generated Alchemite models for a global data set of 300,000 compounds by 500 experimental endpoints, again, targeting some of these critical developing world and neglected diseases. We also looked at models of just the specific project. So something we would commonly do is build a local model tailored to, in this case, just about 500 compounds and 34 endpoints. One thing that was remarkable is, first of all, that The global model gave us a substantial improvement in accuracy when making predictions for virtual compounds. So it was able to learn across that much broader chemical diversity to make much more accurate predictions within this project's chemistry. But also really important is that there was no loss of accuracy in the imputation. Very often, again, with deep learning methods, where you have correlated endpoints, the models improve. But if you throw in uncorrelated or unrelated endpoints, actually it causes the models to get worse. And here we just don't see that. We can actually throw all this data together, and we have a situation of build one global model and run it everywhere on each individual project. Again, we showed a smaller example of that for Constellation. The other thing that we really focus on, and this is another example, is looking at the confidence in predictions, as I say. So just to illustrate that, I have a graph here at the top, which is showing basically, if we look at an independent test set, we're looking at 100% of the test set here, and this is on the y-axis, the root mean square error. So the lower you are on this axis, the more accurate the prediction. If we look at 100% of the test set, you can see the scatter plot here. So it's a pretty good model. We've got a nice correlation here. But as we move left down this axis, we're going to focus on the subset of compounds in the test set that have the smallest error bars, the greatest confidence in prediction. And so if I look at, say, 50%, the most 50% confidence, what you can see is that these snap into the axis. You can see that if we look at the full set, when we remove the compounds, the predictions with the biggest error bars, the lowest confidence, the remaining compounds really do snap into that identity line here, perfect line of prediction shown in orange. And if we go down to the best 10%, what you can see is now all of them lie almost smack bang on this identity line, the line of perfect prediction. There is an interesting thing though. You see this little uptick here. The last few compounds actually have a bigger difference between the predicted and observed value. That's these two data points here circled in green. What you can see here, these are data points that the model is saying, I'm really sure about this. These are good values, yet they don't agree with the experiment. Whereas all the other confident predictions lie right on the line here. So this is an example of those outliers I mentioned before. These are results, experimental results that look highly unlikely based on all of the other evidence that we have. So that's why we can flag up and say, hey, you might want to go retest those because they could be really interesting compounds with better results than you might expect. Continuing up the scale, we also applied the underlying Alchemite method here to a global pharma scale data set. This is about 680,000 compounds and over 1,000 experimental endpoints. This is one of those examples that the data was only about 2% complete across this entire data set. And again, it covered a broad range of drug discovery endpoints, activities, phenotypic screens, ADME properties, high throughput screening, and so on. Again, we have presented a webinar in collaboration with Takeda. We were joined by Scott Rowland, who was then an associate director at Takeda, and was able to explain how they use those results. And one of the things he said is that, this is an extension of what med chemists do. They think very carefully about the relationships between experimental measurements and experimental endpoints and the structure activity relationships and so on. But this is on a vastly greater scale than any person or even team of people could do using conventional tools. And on the right-hand side here, I'm just showing the sort of accuracy. This is just across 100 different target activity endpoints. This is looking at prospective prediction, using the oldest data to predict the most recent data. And what you can see here in blue is the profile of R-squared values for Alchemite. So basically, the higher this is, the better. This is the imputation model. This is just using descriptors, so there's less information, so it's a little bit less accurate, but both of these are substantially better than we use random forest as a baseline to compare here. So you can see the value that that's adding to the quality of predictions for these different endpoints. There's also a preprint of a paper that really goes into all the details behind this study if you follow that DOI. And last of all is an example of combining this with generative methods. So actually looking at generating new compounded ideas and prioritizing those for experimental or for synthesis and experimental measurement. This was a collaboration with the open source malaria project. There's a publication about that last year, but also a webinar that you can view online and hear a lot more detail. But this was looking at modeling sparse anti-malarial activity data. This was actually run as a blind competition by the open source malaria project, and the Alchemite model was one of the best models in that competition. And so the best organizations were invited to then submit generated compound ideas, and the open source malaria project then synthesized and tested those in vitro. We used the NOVA module in Stardrop, and we used the Alchemite model to prioritize the ideas generated around this particular chemical series of interest. I guess the key difference here is that we didn't just suggest the compound that was predicted to be most active. We suggested the compound that was most confidently predicted to be active. So we used those error bars. And of the compounds submitted, the only one that was confirmed experimentally to be active was that suggested by ourselves and our colleagues at Intelligence. Even more exciting is that Matt Todd, the professor leading the open source malaria project, again, he joined us for the webinar. He said that this particular compound is not something that any of the experts, the humans involved in optimizing the SAR would have bothered making. This was a new idea that led the project in a completely different direction and gave them new opportunities for optimization. So this is where that ability to do a very rigorous exploration of chemical space combined with accurate predictions can really add value over an expert staring at the data. Okay, so I've taken you on a bit of a tour through that. I hope I'll come back just for a second to these sort of key points that I mentioned in terms of highlighting high quality compounds in a very proactive way, increasing the confidence in the decisions, make sure we use data that we can trust, and also flag these outliers and potential false negatives that could be hidden opportunities. We've looked at taking the insights and helping to plan and design our experiments and focus on the most valuable measurements. We've shown how we can make more accurate predictions of complex endpoints that in many cases are intractable with conventional QSAR models. And we've shown examples from individual project data sets all the way up to global compound data repositories. So my sort of sales pitch at the end, if you like, if you want to try Sorella yourself, you're very welcome to. We provide different ways to do that. We worked with many different collaborations. I've just shown you a few examples today, but we've done about a dozen different collaborations now, applying Sorella in practice with our customers and our collaborators. We can provide you access to a demo server. In fact, the server that I just used to give a demo, if you want to just try it yourself with this public domain data, you're very welcome to. We'll give you a license for Stardrop if you don't have one available, just to help you to access all this functionality. Or indeed, we can deploy a specific version of Sorella to use with your own data so that you can evaluate its ability to build models of your data and explore all these different applications that we've just described today. So we've talked about the Alchemite method that gains more value than conventional predictive models from experimental data. We've looked at how Sorella enables us to deploy this method for active learning and drug discovery in a very scalable and secure way. And I've given you a few examples of the successful application from sort of project scale to global scale data sets, heterogeneous data across different drug discovery endpoints, combinations with generative methods. And we've even, in other examples, shown how it can be used to predict in vivo endpoints as well. If you'd like to know more, please do let us know. And in the next few minutes, I'll be happy to answer any questions. I can see several questions have already come in, which is fantastic. And so we'll dive straight in. But please do remember, if you have more questions that you'd like to ask, just type them into the question panel in the GoToWebinar control, and I'll be very happy to address as many of them as we can in the time that we have available. All right, so here we go. I'm just going to start at the top and work my way down. So one great question here is it possible to rationalize structurally why Sorella is predicting a certain outcome? So yes, in principle it is. We haven't yet enabled that, to be honest. This is something we call the glowing molecule in Stardrop, which lights up the structure according to the contributions of different functional groups or different regions of the compound. In principle, that is possible with Sorella. It is the sort of one of the next stages of development that we'll be enabling. It certainly can tell you about the importance of individual descriptors, and then you can use that to rationalize, why that prediction has been made. In the meantime, of course, you can understand using that suggestion endpoint how you can see which of the experimental endpoints is contributing most to the prediction of an outcome, and so that can give you quite a lot of information immediately. Next question here: do the purple boxes show up for potential false positives also? Yes, absolutely they do. Apologies, I was focusing on the false negative use case because clearly that's the worst type of error, is missing a potentially good compound. But yes, absolutely, you can see examples where the purple box show up where you've got something that has been measured to be very active and it's saying, oh, wait a minute, this doesn't look very likely. You might want to go retest that. Again, that could be very misleading. Lead you to perform a lot of sort of additional synthesis around an SAR idea that really doesn't pan out. So that is really important. Great question here. Are the curation and validation processes robust enough to ingest any data from your customers and generate good models automatically? I don't suppose there can be any manual curation done on our side. That's, really important. So what we have is a very customizable approach to dealing with that data. So first of all, that query service that I mentioned is written in Python. So any sort of business rules for dealing with that data can be encoded within that query service to ingest the data in the best possible way. You can also provide information about the units of each of those individual endpoints as well, so that Cerella can determine what are the most appropriate mathematical transformations to apply before building a model. For example, many of you will know it's virtually impossible to build a model of IC50 directly because of the heavily skewed distribution. So typically we would take a log transformation or use something like PIC50 as the basis for building the models. So you can specify the units and Sorella will automatically handle those transformations into modeling units. But equally, it will transform the results back out into the experimental units that the users, the chemists, the biologists are most used to dealing with. And so it's really important that it handles all of that behind the scenes. So we've done a huge amount of work to make that a very robust process, because when dealing with these global scale data sets, clearly you don't want to be poring over every column of data individually. How many compounds can be run and visualized in a virtual screening with Cerella and Stardrop? So basically it can scale to any size that you reasonably want. I just used a small data set of 60 compounds running on a very small server. You saw it returned all of those results in just about a second or two. You can scale that across bigger servers to do much bigger data sets. Stardrop itself can handle hundreds of thousands of compounds without a problem, provided you have enough memory on your machine. Just reading down the list. How do the models deal with compounds outside of the applicability domain? Is this information in the statistics, higher uncertainties? Does it make sense to display predictions which are highly uncertain? You've hit the nail on the head. That is exactly what happens when you have a compound that is outside of the applicability domain. That shows up as a big uncertainty in the result, a big error bar on that result. And again, you have a great point. Does it make sense to display predictions which are highly uncertain? The answer is no, it doesn't, and so we don't. Basically, what we do is we look at the probability distribution and we compare that with the range of observed values. If the uncertainty, if the error bar around a prediction doesn't resolve confidently within the range of observed values, then that prediction by definition has no value. It can't help you to choose between compounds. So we don't display that. In that case, you'd actually see an empty cell there. I didn't have an example in the data set I showed you, but you're absolutely right. We don't display results which are too uncertain to be useful. how do I know that Sorella's imputation worked or not? Great question. I showed you some statistics. So hopefully you can see from, for example, the comparison of R-squareds with conventional QSAR methods that it gives substantially better results, significantly better results. And so hopefully those examples at least showed it worked in those cases. But when working with your own data, it is important, of course, to validate those models, double check. And so Sorella will run a validation process as well. You can look at the validation results from those models to check that it is working for your data on the whole. But the other really important thing is to look at those uncertainties, those error bars around each individual prediction. What we've shown in all of the examples, but I just illustrated one, was that where you have a small error bar, the prediction is accurate compared with those predictions that have a big error bar. So what's really interesting is sometimes you can see a model that has very low performance overall on a test set, but within there are still very confident predictions for a subset of compounds that are also very accurate. And you can really focus in on just those that will add value and enable you to make a very good decision. I didn't have an example of that here, but if you come along to the next webinar, we're talking about that collaboration with the University of Dundee. We've actually got some really nice examples of models that typically we would have thrown away and said they're no good. But actually, by focusing on the confident predictions, you can really find very valuable results on which to base your compound optimization decisions. I apologize, there are way too many questions and we're already 5 minutes over time. So I am just going to show one more example. And this actually relates specifically to the constellation example that I presented. So let me just go back to this example here. So someone spotted quite rightly that I've got a highlighted assay result here. This is actually for a cell-based assay, a phenotypic screen. What you can see is in this example here, it basically cannot be predicted with conventional QSAR. This is a negative R-squared, meaning it's worse than random. Whereas the actual Alchemite prediction is very, very good and is able to learn from those relationships between these diverse ADME as well as activity endpoints and make much, much better predictions for this complex downstream experiment. So the question basically relates to that result and says, well, I also demonstrated how we can prioritize the assays to run. Have we actually tried combining the two ideas to select those early assays with which to predict complex downstream experiments? So this is like the example I showed you, but really looking at these very challenging phenotypic screens that are very hard to predict, saying which early sort of higher throughput, maybe biochemical assays and ADME assays we could use. The answer is absolutely yes, we have. We're not able to present the detailed results yet because it's an ongoing project and we need permission from our partner to present it. But we've actually taken this as far as making predictions for in vivo efficacy and showing the in vitro assays that add the greatest value to predict in vivo efficacy. And that's really important because clearly those animal experiments are A, very expensive, and B, we want to minimize the use of animal models. So the ability to run a relatively small number of in vitro assays and make better decisions about which ones to progress in vivo is really important. Great. Well, thank you to everyone who has stayed on the line sort of well past the hour. I appreciate you taking the time. I am just going to remind you that one of these snapshots that I showed you will be presented in much more detail, a collaboration with the University of Dundee, looking at this application of a global deep learning model for global health drug discovery, and really focusing in on how we can actually apply this to make decisions within the context of an individual project. And last of all, just a reminder that the webinar is being recorded. We will post that shortly on our online community site. So if you want to refresh your memory or if you'd like to share it with any of your colleagues, you're very welcome to do so. And if you do have any further questions, please feel free to contact us at info@optibrium.com. We'll be very happy to provide more information And for anyone whose questions we didn't get around to answering, I do apologize, but we will respond by email as soon as possible. So thank you very much, and have a good day.